It's actually really easy.
Is that for circuits too?
Recording in progress.
Good old Bodie parts.
Yeah, Bodie parts are not bad. Once you learn how to do them, you're like, oh, okay, that's not
They
so
look
bad.
really weird, but it's just drawing lines.
It is just drawing lines, and nothing that hard about it.
Yeah, it's like art.
All right, so let's take a look at the lab that y'all have to do tomorrow, and let me give y'all some tips and some hints and some suggestions. It is very open-ended. It's not telling you specifically that you have to do it one way or another. It does have some requirements, but it has some things that you get to choose how you're going to do it. So you're going to be practicing doing state minimization, and you are going to have a sequence detector. So you have a lot of freedom in this lab to create your own design and implementation. By the time you get to lab, you should have considered different design possibilities and worked out the details of the one you chose to implement. So I'm going to give you some suggestions of some things you want to keep in mind, things that will make it harder, things that will make it easier. Construct a state diagram for the following sequence detector. The finite state machine has a 1-bit input U and a 1-bit output F. For each 4-bit input sequence, the output is 0 for the first 3 bits, and then 1 on the 4th bit if the 4-bit sequence matches one of the binary strings 0100, 0110, or 0011. And this is a Mealy type finite state machine. The machine returns to the reset state after each 4-bit sequence. Note that the input patterns do not overlap. So this is a little bit different because there's no overlap. It's not like before we would say if you're supposed to get to 0010, if you started with 1, but then your next one was a 0, you could say, oh, well, I'm at the first 0 of that first 4 bits. That's not how it works. You've got 4 bits, and if your 4 bits match the sequence, then you get an output of 1, and if they don't, you don't. Now, apparently, the way that I thought about doing this when last spring, Dr. Tron watched my video, and he said, oh, I never thought about doing it that way. He said, yeah, that's interesting. That'll work. And so, but it's the same way that I thought about doing it this year, too. So it's the way that I'm thinking about it. And I remember last year that he said, oh, that's interesting. That'll work. I don't know how else you would do it. So that's just the way that I'm going to talk about it. The things that I am going to suggest are one, strongly recommend using debounced button module for clock. And you'll see why when I get it. I'll have to go to my office to get it because I have it in my backpack. But if you think about what you're doing, you've got this sequence. So here's the example. If you do 1001, you're supposed to get 0000, and then you're supposed to start the next 4-bit sequence, and you're supposed to know you're starting the next 4-bit sequence with 1000. Every time you press the button, it's going to be that's a clock signal, but the number of clock signals is really pretty important. And if you want to know where you are, you want to make sure that you're not like double clicking. And I know that the button on the board does that pretty often. So I recommend using the debounced button module. If you don't know what I'm talking about, I'll show it to you. And here's the code you need for that. So when you go to the constraints, these are the constraints that you need for that debounced button. It's the same as the constraints you use for any button or any switch, but it is J1 is the pin. But this is what you want to have for your clock. And while people are getting that down, I'm going to go run it and get the basis board, and I'll show you. It'll be you'll see what I mean. Let me go get the basis board. Chances are, the last thing this morning before I was leaving the house, I tried to change up the program and if you don't use the debounce button, use a switch for the clock. I would not use the button that's on the board. And if you use a switch for the clock, then you just, you switch on and off, and that gets you to a positive clock edge. Not button on board. Sounds like baby on board. Okay, my second big tip is have some way of knowing where you are besides waiting to see if you get a light on the fourth bit. So look at, I don't have it up here anymore, but if you looked at what our sequence was, so we had this long sequence of numbers that you were putting in. I'll come back to this in a second. So this was our example. So you would do 1 0 0 1 1 0, all that. And the only thing that you would definitely see, if you mapped this to an LED, you would see a light here and a light here. And that is the only feedback you would get. That's not going to help you much if it's not working. If you press the button and nothing happens, you have no idea what's going on. Probably the best way to do this, I would think, is make your current state an output and map it to LEDs. Because that's really easy. So how would you do that? So I would say I would have output reg However many states you have, let's say you have between 8 and 15, so 3:0 current state, and then you would map in your LEDs, you would map current state 3 and current state 2 and current state 1 and current state 0 to LEDs. So when you look at your constraints, you would pick the LEDs that you're not using for F, so F is your output, so you would pick 4 LEDs in a row. Might as well pick 0, 1, 2, 3, because then you don't have to change the numbers. And then if you're really lazy like me, rather than calling it current state, call it LED, and then you don't have to change this. So you just call your current state becomes equal to LED, and then you just don't even have to change this. So these would be, you'd put these in your constraints. And you would change LED to current state. And you change all those to current state, and then you will have those lights will light up with the binary value of whatever current state you're in, so you'll know what state you're in. So that is a way to do it, probably a more efficient way than the way I did it, which you'll see, which is, I don't know why I thought that the first thing I thought of was that, but I'll show you. Okay, so tip number 3. Output is tricky. So you're supposed to have a Mealy machine. I would do this there's a couple ways that I would think about doing it. I would have one always block for your next state, and then this would be at current state, comma U, and then you would have another one that would be always at pos edge clock, and this one I would first check value of F. Actually, it doesn't matter if you use non-blocking assignments. So in this always block, make them all non-blocking. So don't use equals, use the less than or equals. And you want to check the value of F and make a current state equal to next state. That still keeps it mealy because you change it based on the conditions that you just found out in your always block, and then you advance it. Another way to do it, besides doing it this way, is in your first always block, determine both next state and next output. So determine both of those in this always block, but you don't actually change the output in this always block. You change it in the second always block. My big tip here is don't do outputs and determination of next state or not determination, display of next state. Display of next state. I'm sorry, don't do display of outputs. Display of outputs, don't display outputs and determine next state. In the same always block. Why? I don't know. I just know that I have been doing this now for a number of semesters. And when the first always block is trying to do the outputs and determine the next state, there's often problems. I don't want to say always, because then one of you is going to be the one that comes to me, mine works, you're wrong. I'm like, okay, fine, all right, fine. It can work. I just know my advice to you is, having seen this a whole bunch of times, it tends to work better when you separate the outputs from the next state. My favorite way to do it, that works for me the best, and it works, and it's what I usually do, is I do, in my one always block, I determine next state and next output. And then in my second always block, I go to the next state and I go to the next output. And that tends to work. This particular one, I didn't do that because on the vending machine, when I did that, some of y'all were told that it wasn't mealy, but it really was mealy, or more. It wasn't. You can do that and still make it mealy or more, however you want to. But this one, I'll show you what I did with that in a little bit. Okay, so that's my next tip. And my last tip, be so careful with your state diagram. And your code for next state. Because if you get one of those next states wrong, it can mess everything up and you'll have no idea why it's not working. So just be very careful with your state diagram. Be very careful that your code matches your state diagram. It's not long code once you decide the way you're going to do it. So I'll show you how I did it, and then I'll show you my board, and then I'll talk about some techniques that you can use. So first of all, this is what I mean by the debounced button module. If you just ask for it in the lab, they have it. And the pin J1, if you're looking at the board, it's the top left, and on the top left, it's the top row. So I put that in the top row of the top left, and then it's the bottom right button. Then okay, so if I think I can hold it up. I think this cord is not that. If you want to see, so what I did is, I forgot my other tip. Make sure you have both an enable and a reset. A reset can be really important. I'll write this down when I come back. So a reset can be really important, because if you lose track of where you are, you'll want to be able to reset. And if you don't have a reset, you're just like in the middle of things. You don't know if you're on the second of 4 or where you are. So I have a reset, and I also have an enable. And so the enable has to be on, and there was a good reason for the enable that escapes me now. But the reset is really important. So I don't know how important the enable is, but the reset is important. And what I did is I had it display in the first LED, the first 7-segment display, if I was at the first of my 4, and then it displayed in the second if I was in the second of my 4, and then the third it displayed a 0 or 1 depending on whether the switch was set. And so, so if I wanted, what's one of our sequences that is on the thing, 0, 0, 0, 1, 1, 0? So it's currently at 0, I press the button, and then I turn the switch to make it 1, I press the button again, I put it back to 0, I press the button, and the LED did not turn on because, why? Because I still have it in reset mode. So let me try this again. 0, 1, and it's also not advancing.
Is your enable on?
I don't remember which switch was enable. Tip, the other tip, remember which tip is enable. Let me look at my code. Let's see. So U is V16, R2 is enable, so it was not enabled.
I just disconnected.
R2 is enabled, V16 is U, and reset is T1. Okay. There, now it's moving. So 0, 1, 1, 0, and the LED lit up. But if I do 0, 0, 0, 0, no LED. 1, 1, 1, 1, no LED. 0, 0, 1, 1, LED. Now, I don't think the lab says that you have to use an LED. You just have to use I think you just have to indicate, you have to have some way to indicate when you have that sequence. Okay, so that's just one example. I don't remember if this is the exact same lab that they did last year or not, but if you search my YouTube channel, I know that last spring I did like 3 or 4 different examples of different things that you could do if you just wanted to look at those and see what they were. So let me write these down. So this is the other big tip. Make sure you have a reset switch. I don't know that enable is important.
I know we used the enable last lab, and it was really important for just like knowing that now it's
Now it's good to
active.
go. Yeah, I mean, it certainly can't hurt anything to have an enable unless you forget which switch is enable.
Yeah.
And you forget to enable it. So it's certainly, so I'll just put on here, consider an enable. Consider an enable.
Does every LED switch come up LED paired? I can't remember how many LEDs there are.
There are an equal number of switches and LEDs, yes.
Oh, and then we just tile in all the switches enabled and whatnot to LEDs.
Yeah, and that makes makes some sense, you still have to remember which is which, but like if you want, like if I have, my enable is R2, and so switch R2 is right below LED L1, and so I could have those two both have the same value, and the way you would do that is you just make LED equal to switch R2, and then that way they have the same light, or they have the same value. Okay, any questions before I start talking about how you're going, some ideas on how to set this up? Okay, well, this is the way that I first thought of it, and it made sense to me that since you have to do 4 in a row, let's just look at the different ways of getting 4 in a row, and because you're going to minimize it, it's okay that we're going to start off with a lot, because we're going to minimize it to whatever the minimum number is. So you'll start with reset, and I called that A. And from reset, you have 2 possibilities. You could get a 0, or you could get a 1. And I called those B and C. And from B, you have 2 possibilities. You could get another 0, so you'd have 0, 0, or you could have 0, 1. And I called those C and D.
You need to, you used
C twice.
Oh, I used C twice. I did, thank you. D and E then. This is what I meant about being oh so careful. Don't do that. D, E. And from 1, you can get 1, 0, and 1, 1. So that would be a 0 and a 1, and we'll call that F, and we'll call that G. This gives us a 0, 0, 0, and a 0, 0, 1. 0, 1, 0, 0, 1, 1. 1, 0, 0, 1, 0, 1. 1, 1, 0, 1, 1, 1. And those would be letters H, I, J, K, L, M, N, O. Now we need to look at what our 4 the sequences that we're targeting. I know one of them is 0, 0, 1, 0. So I know for that one, and we're supposed to go back to reset every 4 things. So I know that from K, if I get a 1, my output will be 1, and if I get a 0, my output will be 0, but either way I'm going back to A. My output is 0 for everything else on here, so I didn't even put the outputs because they're all 0. I think my other ones were 0, 0, 1, 1. Don't count on this being right. Make sure that you check it. So I think 0, 0, 1, 1, so that would be another 1 would be an output of 1, and 0 would be an output of 0. And was the last one 0, 1, 0, 0? I think so. So from J, you'd have an output of 0, 1, and 1, 0. All of the rest of these on this bottom row, all of the rest of these are going to go to A with an output of 0 regardless of the input. Because after you get to 4, you go back to A. So these are all 1, 0, 0, 0. So keeping this in mind, your state table would be, you'd have letters A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. And you'd have U equals 0, U equals 1 for your next state, and U equals 0 and U equals 1 for your output. Seems like this is going to be hard, but it's really not. Where does A go to? B and C. And what's its output? 0, 0. Where does B go to? D and E. And what's its output? 0, 0. Where does C go? F, G. And its output? 0, 0. D goes to H, I. 0, 0. E goes to J, K. 0, 0. Also, okay, I got like almost no sleep last night, so. All right, so let's see. F goes to LM. 0, 0. G goes to NO. 0, 0. Everything else goes to AA. Blah, 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 blah.
And their inputs or outputs are dependent on.
The only ones that have different outputs are I, J, and K.
Oh, okay.
So I was the one that had, and this may be wrong. This is the part where I'm telling you have to be oh so careful. So I was, 1 gave me a 1. So for I had 0, 1. And for J, I had 1, 0. That's not J, that was H. For J, I had 1, 0, and for K, I had 1, 0. And everybody else was 0, 0, 0, 0, 0, 0.
Just for clarity, those numbers are not what's on the lab.
Not what's on the lab?
Because we have like the 0, 1, 1, 0 is the output of 1, 0, 1, 1, 0. So,
No.
so we have, so K goes to A,
K is 0, 1, 1, 0.
and it should be 0, 1, right?
0, 1, 0, 0,
Oh,
0,
yeah,
1, 1,
that's
0,
what
0, 0.
The
Yeah.
output should be 1 at 0
You have those.
from K.
Oh, yeah, so I do have them backwards. Good. And I'm glad I have them backwards because I don't want to be giving you the answers. So for clarity, I said, yes, you have to be super careful. And just to prove that, this is not exactly correct. But I am telling you the only ones you have to really look at are I, J, and K, and those are the ones you have to get correct. And these are not correct. Good.
0, 1, 0.
And probably if you like stick around and ask people, you can figure out what the right ones are. But okay, so then once you have this, your next job, and this is pre-lab, your next job is to minimize these states. So it's not that bad. I will tell you, when I minimized it, it ended up that they mostly were going to be, they were mostly little singletons, so A, B, C, D,
All the way to
E, and then I think F and G, and then I think I and J and K. I think those were all individual, but then I think everything L, M, N, no, H, yeah, H was in here. Let's see. All of these that don't do anything, H, L, M, N, O, those were all together. Because they all go to A. For ones and zeros, they all have 0, 0 as the output. So they end up staying together. You know that J, K, and I are going to be somewhat separate because they have separate outputs. You can tell from your state diagram that A has to be different from everything else, and B has to be different, but I ended up with 9 states. I'm not saying that you will end up with 9 states. You might not. You might come up with a more efficient way of doing it, but I ended up with 9. So let's see.
Oh, I see it. I'm just like clarifying to myself.
I like the way you did the tree.
Thank you.
Yeah.
I like my tree too. I thought when I thought of this, and a year ago, and then when I rethought of it, I thought I think this is easy to see.
It's
easy to understand where you're going.
Yeah, I see why FG are put together, but why DE are different, because the outputs from IJK have different output.
Exactly. When I first did this myself, I did this all in my head. It's like, I know these are all going to be the same, so I just
Yeah.
made a single state. But then when I did it to explain, I thought the tree helped, and then you get to see it,
Yeah.
and you see that, okay, well, F and G look like they're different, but they're not really, because they're all going to things that are doing the same thing anyway. So F and G end up being, I think they end up being
They
the
end up
same.
being, yeah, you put down, they ended
Uh,
up being
in-
it together.
Okay. And then, so then the way I did it, and you're not going to want to copy my code exactly, because if you do, it won't work. And then you'll spend all your time trying to figure out how to fix my code, and that would be better off doing, starting with your own. So first of all, you don't need to have the 7-segment display unless you want it, and you're welcome, you're open to have it if you want. So my AN and SEG were in there just because I like the 7-segment display. I like it because I can look at it and pretend like it means something. My current state and next state were regs. My F, my output, was a reg. And I made parameters for all my states. Sometimes when I'm coding for myself, I don't do parameters, but in this case, in this instance, it was so important to be neat and clean to be able to find the errors, because it's really frustrating when you're ready to test it and you press the button and you're like, okay, nothing's happening, what's going on? And it's helpful to have this so that you'd know what it was. And again, I think it would not be hard at all to, rather than doing it the way I have it here, do this. Okay, so I have so I took out my 7-segment display and I made current state and output, and then we can put in those constraints the way I suggested. Trying to take these out.
If you kept the 7-segment display, do you display it as non-blocking or blocking assignments?
Non-blocking. And then I had my constraints. I wonder if they're still, oh, they were. Non-blocking just means you don't change them until you get to the end of the always.
Until the cycle.
Right. The main thing that you want it to have be non-blocking is the next state. Because you want to make, since it's mealy, you want the output to happen as soon as, like, it's tricky with the way we do it with the clock being a button, but the output happens as you go to A, as you go back to A. Like,
Yeah, it's in between.
right. And so that's why I have it be before you do the next state.
Huh? I didn't know we could do that.
Pretty fancy, huh?
Mm.
All right. All right. So what this does, and what did I put them as? Did I accidentally reuse U16 to V19? Am I using anything twice? No. No. Okay. Okay, so then the way, if you do your constraints, I mean, if you do your state table, your state diagram, in your always block, you're going to want to have, based on your reset, you'll have, you'll want to check that first. And so I just did it as an if reset, then the next state is A, just goes to A, and then everything else was in an else. But I mean, there's different ways of doing it. And I think this is I think I like doing it here better than doing it in the next always block, but you could also do it here. So in the second always block, you could have always begin, if reset, next state is A. Else, you do other stuff. Okay, and then I recommend, rather than doing it the way I have it here, so I have my case based on the current state, that if you, next state is C, else next state is B. I would probably do, and it's just a little bit of extra cut and pasting, I would probably set mine up this way. I would probably have so I would have output reg, and I would have reg next output, and then for each one of these I would have if you begin next state C, next output is 0, end, and then else begin, next state be, or since they're almost all going to be 0 is going to be the output, to have fewer begins and ends. For everything except for IJK, we can do this. So a lot fewer begins and ends. Oh, this won't be hard at all. So do it before the if. So if I'm in state A, my next output is 0, because for whether I'm going, which both of these, the output is 0. And if I'm in state B, my next output is 0. And same for C. And D, also still going to be next output is 0.
Because both, whether it goes to each state, it's both output 0?
Because the only time we get an output of 1 is from states I, J, and K in certain instances. There is no G because F and G got consolidated. Now for I, one of these had an output of 1 and one had an output of 0. And so for I, we would say if U, I don't remember which one it was. For I, the next state is A no matter what. If U, next output, I don't remember if this is right or not. Next output is 1, else next output is 0, and then end. And then something similar for J and K. You figure out which one gets the output of 1 and which one gets the output of 0. I'm just going to make them all the same. Now H, the next output is 0, because H was not one of the ones. And K, I'm just going to copy what I have for I and J. This is not going to work if y'all do it, so anyone who's copying me, it's not going to work. Now you absolutely have to have a default, because you're not using all of your states most likely. So my default next state is 4bxxx. Now I had my logic in here for doing the output. I had it here in the second always block. And I said, if current state was I, if u equaled 1, then the output was 1. Else if, and I actually, for some reason, I had to go through a number of different things to make it work. I originally had these in the first always block, and then I had these as compound statements, if this and that, and I struggled with it. So that's why I think I've always done better with the next output, and so that's why I think that's better than doing these ifs. So we would have f becomes equal to next output.
And that way it's meaty.
It is mealy because we're doing it before we have the next state. Because it's non-blocking, and so we're setting what the output is going to be before it's gone to the next state. So it's not based on the current state. It's not even based on the last state. It's based on the u's, the state and the u's from before. Okay, so it doesn't, it sets it before it goes to the new state. So it says this is what the output is. It doesn't know what the next state is going to be. So the output is based on the current state and the inputs, is why it's mealy. Now I want to see if it works.
Yes.
Okay. Let's see if it works. That would be pretty amazing with my just like doing it and talking at the same time. Any questions while it's thinking about compiling? Now, you absolutely do not have to do it this way. I encourage you to think about different designs and come up with what you think would be best. It might even be a good idea to have different designs ready to go when you go into the lab, so in case one of them just fails completely, that you've got, okay, well, let me try this other one. Especially what I would encourage you to do is to come up with your own idea, be ready to try it, and say, I know I always base mine on what Rebecca did, but I'm going to try my own thing this time. And you can still have mine in your back pocket, like if it doesn't work. And besides, mine might not work. I just realized it was pretty bold of me to just say, oh, well, this is the way that I think you ought to do it without having tested it. Let's see, while we're waiting.
No, it's just like, oh. And then it throws an error at the end. Having a wait, like in between, it's simply lines.
I know, I feel the same way. You know,
Feel the same way?
computers can run, millions of lines of code in a millisecond, nanosecond, and it takes us 5 minutes to upload.
It takes bravado.
It takes bravado, yeah. It's,
Yeah, I was talking with some computer science guy. He graduated in the 90s. Met him at the Happy's run.
I never did back when I was a runner. I always thought about doing that, and I never did.
It's pretty fun.
Yeah.
But yeah, I did the beer mile, and so I got, and the guy who beat me in it in the costume contest was Doc, and he ended up being the computer science guy I talked to, and he was like, yeah, I can imagine a coding language built by electrical engineers being unruly, undocumented, and a pain to deal with.
Yeah.
That's funny.
So back in April 15, 2024, so I have Lab 10 basic setup. If something didn't make sense, you might go look at that. Different implementations in Lab 10 Prelab, so the equivalent of the class today. And it looks like, if I just look at the thumbnail there, that looks a lot like what we did today. And then, so different implementations. I want to show some of the different. Boring. No wonder everybody clicks out of my videos. And
Nobody else-
average watch time 2 seconds.
And then this last button here, last switch, if you have it switched like that, then it represents 1, and that's 0. And then that you have an input every time you press the clock button. And then the LED here will
Yeah,
light up
whatever.
if you've matched the sequence.
Boring.
And now I'll do a sequence of 4 ones. And then you
Ah.
can see the
Oh,
LEDs
wow.
light up to show.
That was smart.
Let's do 1 0 1 0. So there's 1
Oh.
0.
Okay, so rather than showing the state, I have the LEDs showing what
0.
that it shows the actual sequence on there.
The LEDs are they move down to the
I like
so
that.
they push that way. So the first, this one, I don't think I worked all the bugs out of it.
Looks like a health bar.
That's good what it's supposed to. Okay, so now if I do 1 1 1 1. Oh no, I did not work all the bugs out. You can see I don't have all those lit up, but it shows that all the idea here is, oh look, you got the sequence and all the lights flash up, but I didn't finish this one, so it's not doing it at the right time. So it's not completely functional, but that was just to get the idea, to get some sort of signal that you.
What are you doing? I don't want to see this.
There's just different ways that
That's
you
another idea.
can represent the data.
Okay, I think that's all the versions that I have.
Yeah,
I had
okay.
another one that
Oh, yeah.
messed up. It didn't work, but
Well-
I